All engines are engineered for one specific purpose: to convert one form of energy into another. Nowhere is mechanical energy more important than in flight, where thrust is needed to generate lift over the wings and lift the aircraft into the sky. If you've ever seen an airplane, it's pretty obvious where the thrust comes from. These. Like all other vehicle engines, aircraft engines run on the principle of converting chemical energy in the form of fuel into mechanical energy. This kinetic energy is generated by pistons, each linked to a crankshaft. Each piston is in a chamber with an intake and exhaust valve and a spark plug. There are 4 stages to the movement of the piston. During intake, the piston starts moving downwards, the intake valve opens, and a mixture of fuel and air is drawn into the cylinder. During compression, the intake valve closes and the piston starts moving back to the top of the cylinder, compressing the gases. During combustion, the fuel-air mixture is ignited by the spark plug. This causes a tremendous pressure increase in the cylinder and forces the piston downward, away from the cylinder head with a very large force. This in turn turns the crankshaft. The exhaust phase is pretty self-explanatory, opening the exhaust valve as the piston moves back up to purge the cylinder of the burnt gases. The piston moves down again and the cycle begins once more. The horizontally opposed engine configuration is by far the most popular today. These engines always have an even number of cylinders, since a cylinder on one side of the crankcase opposes a cylinder on the other. Fuel, however, usually doesn't ignite itself, so an ignition system is required. In aircraft, a device known as a magneto generates a high voltage. Magnetos contain a rotating magnet, which generates a current in a fixed coil of wire. This current is then broken rapidly, causing its magnetic field to collapse and a large voltage to be produced. The large voltage causes a spark to jump across a spark plug, igniting the fuel. Magnetos are used as they can generate their own electrical energy, thus keeping the ignition independent of the rest of the electrical systems. Thus, the engine continues running in the event of an alternator or battery failure. Most aircraft contain a dual ignition system, with each spark plug having its own magneto. This increases reliability should one fail and improves combustion and power output. Burning of fuel within cylinders produces intense heat, most of which is expelled through the exhaust system. The remaining heat, however, must also be removed as to prevent the engine from overheating. No need to explain why that's not a good idea. Air cooling is accomplished by air flowing into the engine compartments through openings in the front of the engine cowling. Baffles direct air to the hottest part of the engine, primarily the cylinders, which have fins that increase the surface area exposed to the airflow. The air absorbs the engine heat and carries it safely away through one or more openings in the lower aft portion of the engine cowling. But of course, none of this would matter if we didn't have something to burn. Aviation fuel is formed primarily from kerosene and is known as jet fuel A. Naphtha, known as jet fuel B, is another variant, but is usually reserved only for very cold climates due to its low freezing and flash points. It is important to note, however, that the fuel that is actually ignited in the cylinder is a gas mixture of fuel and air. For fuel to burn in a turbine engine, it must be mixed with air in a weight ratio of 1 part fuel to every 8 to 18 parts air. If there is either more fuel or more air than this in the mixture, a flameout will occur. A flameout, as the name suggests, occur when the fire in the engine unintentionally goes out. If the fuel-air ratio is too rich, this causes the fuel temperature to drop below the combustion temperature. This results in a very fast engine acceleration and the flame to go out. This type of flameout is known as a rich flameout. A more common flameout occurrence is the lean flameout, caused when there is not enough fuel for the amount of air flowing through the engine. Low fuel pressure and low engine speeds can also cause this type of flameout. Essentially, the fuel mixture becomes too thin to support combustion and the flame extinguishes. Water contamination is an interesting cause of the lean flameout. At high altitudes, the temperature of the fuel decreases due to the upper atmosphere's lower temperatures. This can cause the dissolved water in fuel to precipitate out and freeze to ice, blocking fuel pipes and starving engines of fuel, as happened on British Airways Flight 38. Aircraft engines are complex and delicate, and having a deep understanding of them ensures safe flying. But try to keep both ice and fire out of your engine, as both might just reduce your enjoyment and your altitude fairly quickly.